helps if you could like and subscribe. If not, please at least just contact these researchers and check the validity of the information that is being delivered here in this video. Maybe share the video with them on an email address and a link. People have told me that I speak way too fast. The vast majority of people, there is a cog button on the YouTube video. If you press that button, you can bring the speed down to half. The visuals that enter your brain go to the brain areas necessary for movement, called the motor cortex, from the Proto-Indo-European word mur, which means to impart movement or pertaining to movement. So what happens is when the visuals go to the areas of the brain necessary for movement, the visuals and the movements are calibrated, which enables hand-eye coordination. So when you type keys on a computer or you use the controls in regards to what you're seeing on the visuals of the screen of a video game, and you press the buttons on the controller to control what is happening in the video game based on your visuals, this is a calibration between the visual areas of the brain and the areas of the brain necessary for movement. And this is so tightly calibrated that it enables us to thread string through sewing needles, which requires very tight calibration between the visuals which enter our brain and the movements that we make, which are coordinated with that. And so what happens with this is the visuals that enter our brains of other people are tightly calibrated with our own motor repertoire. So our visuals enter the brain areas necessary for movement, which puts hand-eye coordination into effect. It enables us to use the visual information to calibrate and coordinate our visual actions. So typing, driving our car in relation to the visuals that we see of the environment to move the car accordingly. Visual motor coordination, hand-eye coordination. And so what happens is when the visuals of others enter our brain, they are bounced off the brain areas necessary for movement in our own motor repertoire. So what we see of others, our brain cells use this information, these visuals, to create an internal reflection that's reflected off of our own motor repertoire. It bounces and ricochets among our own motor repertoire, and the concurrently incoming visuals are being bounced off of the movements, the areas of the brain that we use for movement. In this way, our own motor repertoire is attributed to what we see another person doing, and what we see another person doing is represented in our brain through embodying it, embodying those visuals against our own motor repertoire, which creates a simulation. This is why when you look into mentalizing or how we infer what other people think, when you start to read these studies and you read into this information in the literature, what you will come across frequently is a term called embodied simulation. So by bouncing the visuals of other people's actions off of our own motor repertoire, we are embodying, we are concretizing this information, we are making it real to us. And in this simulation, which our body uses to practice or our brain uses to make a simulation to comprehend other people's movements and actions in a goal-dependent or a social context, based on our own motor competencies and our own motor habits and our own motor repertoire. So what we do, this means our human mirror neuron system is making a comparison of what we do in comparison to what other people do, and it is basically creating, through an embodied simulation of our own motor repertoire, creating a miniature version of ourselves to project onto other people. And this is how we comprehend other people's social actions and intentionalities. The human mirror neuron system, the mirror is something that enables the visuals of ourselves and others to be used as reflections. So you have wing mirrors and you have a rear view mirror on your car. These mirrors can be used to look at the passengers in the back seat or oncoming vehicles. And also the mirror is obviously used for self-reflection. So the neuron is a brain cell. So the human mirror neuron system is the brain cell creating an internal reflection of others. How is that reflection created off of our own motor repertoire? The human mirror neuron system uses the visuals of others and sends those visuals to the brain areas necessary for movement, and then attaches and overlaps and is integrated with what's called the default mode network. The default mode network is a conjugation of all the brain areas across our entire brain. And so what that means is this is where our autobiographical, emotional, episodic, semantic, declarative forms of memory come from. This is also where our emotional feelings are felt. And this is also where our internalized contexts can be drawn and our internal calculi are used to work out what other people's actions mean. And so when the human mirror neuron system has bounced the visuals of other people's social actions or goal-dependent actions or what other people are doing in any actionality off of our own motor repertoire, what is then happening is we are attaching our own internalized context, our internalized schemata, and our internalized calculi used for calculating and working out what others' actions mean in a social context. This is automatically done by the human mirror neuron system. It's automatically as hand-eye coordination occurs. You don't have to think, let me move my finger over to this key and press this key here on my phone. This is hand-eye coordination. This is tightly calibrated with the visual. The motor area is activated also. With the visual of another person, the motor area is activated also. This happens just as automatically. The default mode network then attaches the self-referential internalized context of autobiographical self-relevant information. What does this do as a conjugation? This causes us to necessarily self-project our own internalized information onto other people, which is very useful in the information that's within our brain, which is used to work out and infer what other people's social actions mean, because we can only use the information available in our brain. We can't directly connect to the brains of other people. We are not mind readers. If we were, games like poker would not exist. We couldn't. There's a lot of games that people play that would change drastically if we could actually connect directly to the sensory evidence of other people, and then we'd know exactly what they're thinking. We are making inferences, high-level inferences, and low-level embodied simulations to infer what other people think. And the embodied simulation is the human mirror neuron system, whereas the high-level inference is done by the default mode network, by the connection, the overlap between the human mirror neuron system and the default mode network we're in. There is this integration between these two networks. The retina is the area of the eye where light hits, and then this light is translated into a neural visual signal, which enables our brains to see. The central portion of the retina is responsible for central vision, and that is called the macula. The fovea is where visual acuity is highest. According to researchers at the Neuro-psychology departments for the Brooklyn University, Males average 38% more of this central visual macular photopigment. Now you can see below here we have a graph of the retina, and you can see this pigmented epithelium. This is the photopigment that is necessary for converting light into neural visual signals, which enables our brain to see. Males have 38% more of this pigment on their retina than females. What this means is males have 38% more central visuals being shown to their brain of the external environment. So males have a 38% stronger central visual reliance, a central visual reliance, which is 38% heavier. Now, this is what enables the photoreceptors of the rods and the cones to then become activated, because this pigmented epithelium, or this central visual macular photopigment, is what converts from an 11-cis state to what's called an all-trans state, which enables the brain to it enables the visual transduction cascade to commence, to begin. And this means that males are going off a much heavier central visual. Now, what does this mean in terms of the human mirror neuron system, where visual and movement calibration is so tight that it enables us through the visual motor calibration and hand-eye coordination to thread string through a sewing needle? That's very tight hand-eye coordination. That's a very tight calibration between the eye's visuals supplied to the brain and the motor output that moves the hand in calibration with the visuals. That's tight hand-eye, tight visual motor coordination. The word motor from the Proto-Indo-European word mur, which means to impart motion or to control, so it controls motion, or a prime mover. Or it means to move. And so what happens when the human mirror neuron system and the visual motor repertoire is made from 38% stronger central visual reliance? How will the male then be able to comprehend the female? And how will the female's human mirror neuron system comprehend the male, the other half of the world, given that roughly half of the world is made up out of males and the other half of the world is made up out of females? Well, those signals from the rods and cones and the central visuals that the males have, 38% more of than women, then go to the retinal nerve fiber layers after they leave the retinal ganglion cell. Now, the retinal nerve fiber layers are the axons of the retinal ganglion cells. And what the retinal nerve fiber layers do is they bring the visual signals, which are starting with and connected to the rods and the cones of the eyes, to the brain, to the primary visual cortex, which is where our brain first becomes consciously aware of seeing anything that we're seeing, period, of the visuals of the world. The word primary means first. It's the first visual cortex. It's the first visual area of the brain. From here, you have the retinal nerve fiber layers, which, as we just looked at above, are the nerves that take visuals from the retina. So the central portion of the retina is the macula. The macula is responsible for central vision. The fovea is the highest visual acuity of the macula. The retina nerves carry the visuals from the retinal ganglion cells, which begin with the rods and cones, to the brain so we can see. These retinal ganglions are attached significantly more to the peripheral visual field in females. And so if you look at this picture here, what you can see is that visuals from the left side of the temporal visual field hit the retina, and you can see this curving along the eye, this curvature, this line that's drawn parallel to the circuity or the curvature of the eye. And what you can see is that is where the light is hitting the retinal nerves and then being carried to the brain. And this curvature persists even from, yes, the nasal and temporal, the central and the sides of the visual fields, as well as the superior upper and the inferior lower parts of the visual fields. These retinal nerves relations, they persist. But what we have here is a study from set-specific differences in the circumpillary retinal nerve fiber layer thickness from the Center of Civilization Diseases and the Eye Research Institute from Harvard School of Medicine, Boston, Massachusetts. And what this shows is females are found to have significantly higher retinal nerve counts at the superior temporal and at the nasal, but also the temporal and inferior temporal. Now, we said that inferior means lower and temporal meaning the sides of the visual fields. And so inferior temporal is the lower side of the visual field diagonally. Temporal is the central midway. Superior temporal is the upper. And then we have the nasals, which is the central because it's in line with our nasal, which is the center of our cranium, the center of our head. So this is from a large population-based study. And what you can see here is there's over 5,000 participants, of which roughly half of them are females, and the global circumpillary retinal nerve thickness is significantly higher in females compared to males, and this is consistent with previous studies. And what you find is there is a 9.98 micrometer increased thickness in females, and in perspective, the difference of 9.98 micrometers equates to 31 years more of having a retinal nerve fiber, because the retinal nerves decline by 0.32 micrometers every year by 0.32 micrometers. So a 9.98 micrometer difference is a highly significant difference, and you find that at these different visual fields. And as you can see here on the eye, when you photograph the back of the eye, when you go for a visual test, they're looking at the lens, the cornea, and one of the things they're doing when they photograph your eyes, they're looking at a difference in, they're looking at your retinal nerve fiber layers, because this tells them about the areas of your visual fields that you can see with and the areas of your visual fields that you will have issues with, because as we saw in that diagram earlier, the temporal and the nasal halves of the visual field are represented in the opposite sides or the contralateral retina nerves of the eye of the retina. And what happens here is when these nerves thin, or when you have less of these nerves to take the light signals from the retina to the brain, then the brain doesn't see those areas of the visual field, and that's where you get visual defect. And just to clarify, sight is different from vision. Sight is not your brain's interpretation. The visual or vision is your brain's interpretation of sight. This is what your brain is actually able to process. So vision is all that really matters when it comes to being able to actually see the environment, is the visual functionality or fecundity or competency. And so what we're looking at here is the retinal nerve fiber layer difference and this is again another chart from the researchers at the Eye Institute at the Harvard School of Medicine, Boston, Massachusetts. What we're looking at here is this chart that's given is the temporal and the superior temporal, the nasal, the inferior nasal, and inferior temporal. These areas are all significantly higher in females. As you can see, this is the females represented in red. Here's the blue for the male. So what we're looking at is around a 40% greater amount of peripheral visuals in females, and there's moderation in different areas of the visual field. We're looking at around a 40% increased peripheral visual difference inside of females, and in males we're looking at a 38% increase in macular pigment on average, which is not quite 40%, but it's close. And males have a slightly deeper and narrower foveal pit, which equates to more central visuals. So what we have here is about an 80% difference between males and females. We have a fourfold difference. The difference between 80% and 20% is 20 times 4 is 80. So we have a 80% or fourfold difference between the central visuals that males see and the heavier central visual reliance that males have versus the peripheral visuals that females are seeing from their retina. So the male has 38% more of the central visuals bias in their visual attention to the central visual alignment, whereas the peripheral visuals are blocked out 40% more. Now in total, that's about fourfold greater increase. What we have with females is females are not biased to the central visual field, and they're taking in the peripheral visuals. So when the human mirror neuron system is being supplied from the information that their eyes are sending to their brain, that their brain interprets as vision, and then these visuals are then calibrated with the movements, you then end up with and please feel free to read through the information on the screen so you can see the difference between the micrometers and the difference in the standard deviation of 16 or 14 from a base of 70 or of 84 micrometers. That equates to moderate to severe to very severe visual impairments. And you'll find this is consistent across studies. This is why they, when you pay for the visual test at your opticians, they take a picture of your retina nerves. And so what we have is what you'll find is that a male has much stronger reliance on the central visuals. And what that does is that means that his human mirror neuron system first doesn't know that he's gawking. It doesn't know that he's gawking because the visual motors, the visual motor coordination is tightly calibrated so that our movements correspond with the visuals that we receive that go to our motor cortex. So for a male to look directly with the central visual field, to look with fourfold more reliance on the central visual to extrapolate that social information is not unnormal for a male. It is natural. It is the way that his brain sees the environment. It is automatic. It is physically natural. That is the way that the central visuals work. And then if it comes to the peripheral visuals, for a female whose human mirror neuron system is embodying this, who's taking the visuals of the male, staring at her and gawking at her and ogling her, ogling from the Proto-Indo-European word OKW, ok, where you get the word ophthalmic or optical or optic or opsis, or also ogle. The word ok is the Proto-Indo-European word. It's the etymological, factual, actual, true definition. It differs from a socially colloquial definition. This is the actual factual definition, and it means the eye and to see with the eye. So this ogling, which is in the form of something called stereopsis. Also, you get the word stern if you add an N on the end of the word steer. Stereopsis is called depth perception. It's another name that it goes by, and this is it's also where you get the word from the word steer. So males, stereopsis means to opsis from the word op means to use the eye to see, and steer, which means firm and hard, because steering is a firm, hard way of looking to see. It means to use the eye to see firmly and hardly. And why does that happen? Because stereopsis occurs only in the central visual field. You can only do stereopsis with central vision. Ask the opticians; they will tell you. Ask the experts; they will tell you. Stereopsis, also called depth perception, can only be done by using the central visual field. It cannot be done with the peripheral visual field. And so what happens here is males have much higher stereopsis and depth perception. Why? Because males have a fourfold stronger reliance on the central visuals. So males steer to see. And there's a lot more that we're going to get into. But for now, I would say if you go to your kitchen and you grab the kitchen roll tubes that your tissues are wrapped around in your kitchen, and you were to take those kitchen roll tubes and you were to hold them up like little binoculars and look through them, while you're sitting down, don't walk around, don't bump into people, don't do anything clumsy, because if your visual field's reduced and you can't see the environment, you might not move accordingly in the environment, you can cause an accident. So do it while you're sitting down and look around at the people in the room, and you will see that you need to look directly with undivided central visual attention to see the people's faces, to see how people are reacting to the sight of you, to do an embodied simulation and attach internal context in them to infer what they're thinking, to infer how they're reacting or how they're responding while you're communicating, etc. That's what you will see happens if you use the central visual. Just by looking down at something that's cheap, it's affordable, you're going to throw the tubes away anyway. This way, you're making them worth it. Whereas in otherwise the tubes, they don't have any worth. You're just going to throw them out. So the central visual degrees, the central visual field is 0 to 15 degrees. How do we know that? Because researchers stimulate the fovea, which is the central portion of the macula. The central portion of the retina is the macula. The fovea is the area of the macula with the highest visual acuity. They stimulate the fovea and they check the corresponding neurons, which are neuronal populations, which are brain cells, and they see which are locations that are activated by using the central visuals. So by seeing which areas are located by using the central visuals, researchers know that the central visual field is activated only when the fovea or the central visual area of the macula is stimulated up to 15 degrees. So beyond there, you're now outside the macula, you're outside of the range of central vision, and now you've gone into peripheral vision. Peripheral vision goes up to 60 degrees. 15 times 4 is similar to 20 times 4 in that males have about 80% heavier reliance on the central visual field. The central visual field is 15 degrees, times that by 4 and you're in the peripheral visual field. Again, women have 4 times more. That matches well with what we can see from the eye anatomy and how it sends visuals to the brain. So females have fourfold more of the global peripheral visuals. And as you can see here, this study is from Life Sciences and the School of Mechatronics and Automation. We have the email addresses for the authors. So as you can see here, as a stimulus moves from the fovea to the periphery, the locations which are corresponding in the brain, they go from the posterior, and that's pertaining to the fovea respectively, to the anterior portions of the calcarine sulcus, which is corresponding respectively to the peripheral visuals, as you can see here. And this calcarine sulcus is a site in the human primary visual cortex. We said primary means first. And this is a similar demarcation process, which is used to outline V1, which is the primary visual cortex,